Hello and welcome everyone. This is Pradeep Bhandari. In this session, we will discuss one of the most important concepts of information security, that is cryptography. Main aim of this session will be: number 1, understanding the concept of cryptography; number 2, understanding types and cipher models of cryptography. So let's start our discussion with the concept of cryptography. Cryptography, a word with Greek origin, means secret writing. However, we use the term to refer to the science and art of transforming messages to make them secure and immune to attacks. Although in the past cryptography referred only to the encryption and decryption of messages using secret key, today it is defined as involving three distinct mechanisms. These are symmetric key cryptography, asymmetric key cryptography, and hashing. We will discuss symmetric key cryptography, asymmetric key cryptography techniques in this session. Cryptography involves hiding the contents of a message by enciphering. Another technique that is used for secret communication is steganography. That word steganography, with origin in Greek, means covered writing, in contrast with cryptography, which means secret writing. Steganography means concealing the message itself by covering it with something else. We will discuss mainly cryptography here. So now let's discuss symmetric key cryptography first. Symmetric key cryptography is also known as traditional cipher. In symmetric key cryptography, same key is used for encryption and decryption. Symmetric cipher model. A symmetric encryption scheme has 5 main components as shown on the screen. Number 1 is plain text. This is the original understandable message or data that is fed into the algorithm as input. Second component is encryption algorithm. The encryption algorithm performs various substitutions and transformations on the plain text. Third is secret key. The secret key is also input to the encryption algorithm. The key is a value independent of the plain text and of the algorithm. The algorithm will produce a different output depending on the specific key being used at the time. The exact substitutions and transformations performed by the algorithm depends on the key. Fourth component is ciphertext. This is the scrambled message produced as output. It depends on the plain text and the secret key. For a given message, two different keys will produce two different ciphertext. That ciphertext is an apparently random stream of data depending on secret key. Fifth component is decryption algorithm. This is essentially the inverse of encryption algorithm. It takes the ciphertext and the secret key and produces the original plain text. Figure on the screen represents the concept of symmetric cipher model. In this model, plain text is used as input. We convert the plain text into ciphertext by using encryption algorithm and key. On the receiver side, ciphertext is converted into plain text by using decryption algorithm and key. Sender and receiver share the same secret key. There are two requirements for secure use of conventional encryption. First is, we need a strong encryption algorithm. This requirement is usually stated in a stronger form. That is, the opponent should be unable to decrypt ciphertext or discover the key even if he or she is in a possession of a number of ciphertexts together with the plain text that produced each ciphertext. Second requirement is, sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. If someone can discover the key and knows the algorithm, all communication using this key is readable. On the sender side, encryption algorithm works on the message P and the encryption key K to produce ciphertext C. We can write it as shown on the screen. Ciphertext is equal to the encryption function of key and plaintext. On the receiver side, decryption can be performed as shown. Decryption function D of key K and ciphertext C, where P is equal to plaintext, K is equal to key, and C is equal to ciphertext. The two basic types of all encryption techniques are substitution and transposition. Let's discuss substitution cipher techniques. In substitution cipher technique, letters of plain text are replaced by other letters. If the plain text is viewed as a sequence of bits, then substitution involves replacing plain text bit patterns with ciphertext bit patterns. To write down a key for the substitution cipher, we first write down the alphabet and then a permutation of the alphabet directly below it. This mapping gives the substitution which is to be made for each respective character in plain text to make the ciphertext. Plain text alphabet and the ciphertext alphabet are as shown on the screen. Encryption involves replacing each letter in the top row by its value in the bottom row. Decryption involves first looking for the letter in the bottom row and then seeing which letter in the top row maps to it. Hence, the plain text word HELLO, that is hello, would encrypt to the ciphertext ESVVJ if the mentioned substitution is used. The number of possible keys is equal to the total number of permutation of 26 letters. Substitution cipher can be of two types. First is monoalphabetic and second is polyalphabetic. As the name suggests, if the substitution is done uniformly, that is called a monoalphabetic cipher or simple substitution cipher. In simple words, we can say in monoalphabetic substitution, an alphabet is replaced with the same alphabet in the entire text. In polyalphabetic substitution, different substitutions are made depending on where in the plain text the symbol occurs. This is called a polyalphabetic substitution. It means the same character can be replaced with different characters in the text. For example, A can be replaced with D and B in different places of occurrence. Modern symmetric key. Now, these algorithms can be divided into two categories, that are stream and block ciphers. In a stream cipher, encryption and decryption are done one symbol at a time. We have a plain text stream, a ciphertext stream, and a key stream. Call the plain text stream P, the ciphertext stream C, and the key stream K. Example of stream cipher is one-time pad. Block ciphers. In block cipher, a group of more than one plain text symbols are encrypted together, creating a group of ciphertext of the same size. Based on the definition, in a block cipher, a single key is used to encrypt the whole block even if the key is made of multiple values. In a block cipher, a ciphertext block depends on the whole plain text block. Example of block cipher is DES, that is data encryption standard. Let's move on to second type of cipher known as asymmetric key ciphers. In asymmetric key ciphers or cryptography, two different keys are used. These are public key and private key. The concept of asymmetric key cryptography evolved from an attempt to attack two of the most difficult problems associated with symmetric encryption. The first problem is that of key distribution. Key distribution under symmetric encryption requires either that two communicants already share a key which somehow has been distributed to them, or the use of a key distribution center. Whitfield Diffie, one of the discoverers of public key encryption, along with Martin Hellman, both at Stanford University at that time, reasoned that this second requirement negated the very essence of cryptography, that is, the ability to maintain total secrecy over your own communication. The second problem that Diffie considered, and one that was apparently unrelated to the first, was of digital signature. If the use of cryptography was to become widespread, not just in military situations but for commercial and private purposes, then electronic messages and documents would need the equivalent of signatures used in paper documents. Now, the question arose, can a method be devised that can authenticate the identity of the sender of a particular message? Public key cryptography works to provide a solution to this problem. Now we look at the overall framework for public key or asymmetric cryptography. Then we examine the requirements for the encryption or decryption algorithm, which is at the heart of the scheme. Asymmetric algorithms rely on one key for encryption and a different but related key for decryption. These algorithms have following important characteristics. It is computationally infeasible to determine the decryption key given only knowledge of cryptographic algorithm and the encryption key. In addition, some algorithms such as RSA also exhibit the following characteristic. Either of the two related keys can be used for encryption with the other used for decryption. The main components of asymmetric key cryptography are as shown in the figure. Plain text. This is the readable message or data that is fed into the algorithm as input. Encryption algorithm. The encryption algorithm performs various transformations on the plain text. Public and private keys. This is a pair of keys that have been selected so that if one is used for encryption, the other is used for decryption. The exact transformations performed by the algorithm depend on the public or private key that is provided as input. Ciphertext. This is the scrambled message produced as output. It depends on the plain text and the key. For a given message, two different keys will produce two different ciphertexts. Decryption algorithm. This algorithm accepts the ciphertext and the matching key and produces the original plain text. The essential steps are as shown. Each user generates a pair of keys to be used for the encryption and decryption of messages. Each user places one of the two keys in a public register or other accessible file. This is called the public key. The companion key is kept private. As figure suggests, each user maintains a collection of public keys obtained from others. If Bob wishes to send a confidential message to Alice, Bob encrypts the message using Alice's public key. When Alice receives the message, she decrypts it using her private key. No other recipient can decrypt the message because only Alice knows Alice's private key. With this approach, all participants have access to public keys and private keys are generated locally by each participant and therefore need never be distributed. As long as a user's private key remains protected and secret, incoming communication is secure. At any time, a system can change its private key and publish the companion public key to replace its old public key. To discriminate some of the important aspects of symmetric and asymmetric cryptography, we refer to the key used in symmetric encryption as a secret key. The two keys used for asymmetric encryption are referred to as the public key and private key. Invariably, the private key is kept secret, but it is referred to as a private key rather than a secret key to avoid confusion with symmetric encryption. Table as shown on the screen compare the symmetric and asymmetric cryptography. Symmetric cryptography uses the same algorithm with the same key for encryption and decryption. In asymmetric cryptography, one algorithm is used for encryption and decryption with a pair of keys, one for encryption and one for decryption. In symmetric cryptography, the sender and receiver must share the algorithm and the key. In asymmetric cryptography, the sender and receiver must each have one of the matched pair of keys. In symmetric cryptography, the key must be kept secret. In asymmetric cryptography, one of the two keys must be kept secret, other can be public. In symmetric cryptography, it must be impossible or at least impractical to decipher a message if no other information is available. In asymmetric cryptography, it must be impossible or at least impractical to decipher a message if no other information is available. In symmetric cryptography, knowledge of the algorithm plus samples of ciphertext must be insufficient to determine the key. In asymmetric cryptography, knowledge of the algorithm plus one of the keys plus samples of ciphertext must be insufficient to determine the other key. Let us take a closer look at the essential elements of a public key encryption scheme as shown in the figure. Here y is equal to E, which is a function of private key of A and X, and y is equal to E, which is a function of public key of A and Y. There is some source A that produces a message in plain text, x is equal to x1, x2, so on up to xm. The m elements of x are letters in some finite sequence. The message is intended for destination B. B generates a related pair of keys, a public key referred to as PUB and a private key referred to as PRB. PRB, that is private key of B, is known only to B, whereas PUB is publicly available and therefore accessible by A. With the message X and the encryption key PUB as input, A forms the ciphertext as Y. The intended receiver in possession of the matching private key is able to invert the transformation by using x is equal to decryption, which is a function of private key of B and Y, and challenger observing Y and having access to public key of B but not having access to private key of B or X must attempt to recover X and private key of B. It is assumed that the challenger does have knowledge of the encryption and decryption algorithms. If the adversary is interested only in this particular message, then the focus of effort is to discover X by generating a plain text estimate. Often, however, the challenger is interested in being able to read future messages as well, in which case an attempt is made to recover private key of B by generating an estimate PRB. We mentioned earlier that either of the two related keys can be used for encryption, with the other being used for decryption. This enables a rather different cryptography scheme to be implemented. Whereas the scheme illustrated here provides confidentiality. Now the figure on screen reveals the use of public key encryption to provide authentication. Now in this case, A prepares a message to B and encrypts it using A's private key before transmitting it. B can decrypt the message using A's public key. Because the message was encrypted using A's private key, only A could have prepared the message. Therefore, the entire encrypted message serves as a digital signature. In addition, it is impossible to alter the message without access to A's private key. So, the message is authenticated both in terms of source and in terms of data integrity. In the preceding scheme, the entire message is encrypted, which, although validating both author and contents, requires a great deal of storage. Each document must be kept in plain text to be used for practical purposes. A copy also must be stored in ciphertext so that the origin and the contents can be verified in case of a dispute. A more efficient way of achieving the same results is to encrypt a small block of bits that is a function of the document. Such a block, called an authenticator, must have the property that it is infeasible to change the document without changing the authenticator. If the authenticator is encrypted with the sender's private key, it serves as a signature that verifies origin, content, and sequencing. It is, however, possible to provide both the authentication function and confidentiality by a double use of public key scheme by using functions as shown on the screen. You can observe this scheme from the figure. In this case, we begin as before by encrypting a message using the sender's private key. This provides the digital signature. Next, we encrypt again and using receiver's public key. The final ciphertext can be decrypted only by the intended receiver, who alone has the matching private key. Thus, confidentiality is provided. The disadvantage of this approach is that public key algorithm, which is complex, must be exercised 4 times rather than 2 in each communication. Applications of public key cryptosystem. We can classify the use of public key cryptosystems into 3 categories: encryption and decryption. The sender encrypts a message with the recipient's public key. Digital signature. The sender signs a message with its private key. Signing is achieved by a cryptographic algorithm applied to the message or to a small block of data that is a function of the message. Key exchange. Two sides cooperate to exchange a session key. Several different approaches are possible involving the private keys of one or both parties. So, symmetric and asymmetric ciphers will exist in parallel and continue to serve the community. We actually believe that they are complement of each other. The advantage of one can compensate for the disadvantages of the other. The conceptual differences between the two systems are based on how these systems keep a secret. In symmetric key cryptography, the secret must be shared between two persons. In asymmetric key cryptography, the secret is personal, that is unshared. Each person creates and keeps his or her own secret key. I hope you must have understood the concepts of ciphers. Wish you happy learning. See you in the next session.